Okay, welcome to the second session of the day. So you heard this morning about classical algorithms, and today we're going to fight back, or this session we're going to fight back with quantum algorithms. And our first speaker is Fernando Brandao, who will tell us about quantum algorithms for semi-definite programs.
Thank you, Aaron. Hi, everyone. So this is joint work with Chris War, also known as Chair of QIP 2017. So it's okay. We have a common goal here, all of us, with our experimental friends. We want to one day build a quantum computer, right? So, and we have, as theorists, we like to understand what we use the quantum computer once we have one, and we learn a lot about that in the past 20 years. We know sometimes we can have exponential speedups. There are many great applications like simulate quantum physics or just factor really big numbers. Then sometimes for other problems, we have more modest speedups, but they're still interesting. For example, searching, Grover's algorithm, and we have a bunch of other examples. And there's also things that we understand less that there might become relevant applications of a quantum computer, but maybe we have to wait until we have one to figure it out. And that's like many heuristics that we know. For example, quantum annealing or adiabatic optimization and so on, which are promising, but we really don't have the theory to analyze how well they perform, and we don't have the quantum computer yet to test them. And the point of this talk, what I'd like to tell you, is that solving semi-definite programming belongs to these two last categories. So we can have polynomial speedups, and I hope I can convince you that it's a promising heuristic to run on a quantum computer as well once we have one. Okay, so what is semi-definite programming? It's, oops, wait, there is a problem. The equation didn't appear. Oh, just a second. Oh, my computer, there's a volleyball beach here. I'm sorry, you'll have to restart my PowerPoint. Yeah, I should be using like Microsoft products, not Apple. That's the problem. But let's see. Yeah, right. So, semi-definite program is a class of convex optimization problem. And it's very simple. Basically, just want to optimize a linear function with some linear constraints over the set of positive semi-definite matrices. So the objective function is maximum of trace Cx. C is just a square matrix. X is another square matrix, which is the variable we optimize over. And then we have a bunch of linear constraints. We have M linear constraints, and they are all of the form trace AJX is smaller than BJ, where AJ are other matrices and BJ are real numbers. And the PSD constraints, x bigger than 0, just says that x is Hermitian, and all the eigenvalues of x, they are bigger or equal to 0. So what are the parameters? The inputs, they are n by n S sparse matrices, C1, A1 up to AM. Each one is n by n, and we assume that they're all S sparse. So in each row, we have at most S non-zero elements. And we have a bunch of real numbers, B1 to Bm. And the output, we want to just find x, which optimizes this linear function. So there's a special case where all the matrices are diagonal. This is linear programming. Both SDPs, semi-definite programming, and LPs, they are very useful. There are many applications, like in combinatorial optimization, operational research, and so on. I don't have actually to tell you that they're very useful because, right, we use them all the time, right, in our fields. And well, one simple reason is just because the fundamental object that we work with all the time, density matrices, right, they have a central role, right, in SDPs, at least like non-normalized density matrices. And also, why they're so useful? Well, because we actually have pretty good classical algorithms for SDPs. So the most used one is interior point methods. There are many different interior point algorithms, but so the best rigorous runtime is of this order, like m squared ns, roughly, and it scales like log 1 over delta. Delta is the error. There is also another class of problems which is less used in practice, but it's also interesting and will be very relevant for this talk. It's called multiplicative weight method. And it has a better dependence in terms of m, in terms of m and other parameters. There is also some, we'll get to that later. There is the width and the size of the solution parameters which are relevant, but it has a worse scale in terms of the error. Okay, but we'll get more to that. And the question we want to address is whether there are quantum speedups for SDPs and LPs. I think that's a natural question, but the people didn't explore it so far, and this is what we want to do. So before telling you the results, let me just define a few other concepts about SDPs. One is, okay, what I present to you is called sometimes the primal problem, right? This is just want to maximize trace Cx over a bunch of constraints, m constraints of the form trace aj x smaller than bj, and x being positive semi-definite. But there is also a dual program, a dual SDP, and it has the following form. We just want to minimize the inner product of b with y, right? So just sum over I, bi, yi. And then we have just one positive semi-definite constraint as well, but now it's of the form of sum over j, yj, aj bigger or equal to c, the matrix C. And now we require that the vector y is a vector, now is an m-dimensional vector. Component-wise, all the components are bigger or equal to 0. Okay, so that's a different SDP, right? And the point is that under mild conditions, not always, but pretty much like almost always, and we assume that the SDPs that we work with, they have this property, the solution of the primal is equal to, the optimal value of the primal is equal to the optimal value of the dual. So you can choose which one you want to solve, the one which is more convenient to you. And we are going to explore that. So last two parameters that I have to introduce before going to the results. As this multiplicative weight method does, and as our algorithm will do, it also depends on two other parameters, apart from the sparsity and the size of the matrices and the number of constraints. These are, like you can call the parameters related to the size of the solutions, the optimal solutions. So suppose we have an optimal primal solution, you can pick any one you want if there is more than one. The R parameter is just an upper bound on the trace of the optimal solution of the primal program. Okay, so this matrix is positive semi-definite, so this trace is the same as the one norm. So it tells us how big the one norm of the optimal solution is, like the Schatten one norm. The dual will do the same thing, but now is a vector, the optimal solution, so we care about the one norm of this vector. Okay, and the small r parameter just tells us how big it is. All right, so before getting to the results, let's do some limitations on what we should be able to achieve. So first, if you just want to write down the solutions, the optimal solution of the primal problem is an n by n positive semi-definite matrix. So this requires roughly n square parameters, right? So that's, if you want to write down the solution, you need at least that. For the primal, you need at least m, or the m time. But suppose you want to do something less. We just want to compute the optimal value. We don't care about writing down the optimal solutions. Then we still have some lower bounds. So there is an easy reduction to search problem. I'm not going to give the details, but let me just mention the results to compare with the performance of the algorithm later. So there's a classical lower bound of order n plus m, okay? And all the other parameters, the r, the small r and big R, and the sparsity s and the error delta, they are constants. Then you still need time n plus m classically. And quantum, you still need times square root of n plus square root of m. We don't know if that's optimal. There is also a poster this afternoon by Appledon, Gillian, Gibbs, and De Wolf, and they improve these results so they can get sharper results like of order n times m, when m is roughly equals to m, but with everything constant, but not the small r parameter. Okay, and that will be relevant, but I encourage you to see their poster later on. So what are the results that we get? So the first result is that there is a quantum algorithm for solving SDPs, and the runtime is square root in n, the size of the matrices, is square root in m, the number of constraints, square in the sparsity, and some polynomial in some log n m, and in this r, capital R, small r parameters, and in the error. And I'll tell you what this, we have some bounds on this polynomial. It's pretty bad, but I'll get to there. So what is the input? Again, is an n by n S sparse matrices, C, A1 to M, and the real numbers. We assume this normalization, that's the operator norm of AI and C is smaller than 1. If you don't, it's fine, but then we just have to, there will be an extra term in the complexity related to the size of the norms. And what is the output? Okay, so because we have sublinear complexity in n and m, we should not be able to write down the optimal solution, right? So we have to be happy of doing something less than that. And what we require from the algorithm is that apart from estimating the optimal value, we are just able to sample from a probability distribution. Oh, this should be one norm. Okay, so a probability distribution equals to y divided by the one norm of y, right? Such that it's normalized. Sorry, this is a type. And the value of the one norm, and quantum samples from a quantum state, which is just the normalized optimal solution, and the value of the trace. Okay, so and of course we want to estimate the optimal value up to some additive error delta. So the output form, if you remember the HHL quantum algorithm for linear equations, has a similar flavor, right? We output the solution as a quantum state. Here we output the solution either as a probability distribution or as a density matrix, depending on if you want to solve the primal or the dual problem. Okay, so that's the details. Okay, but now how we access the matrix, right, C and A1 to AM, we assume that we have the normal setting in query complex. We just have an oracle which outputs any chosen non-zero entry of these matrices at unit cost. So we just have 4 indices, J, K, L, Z. J labels the choice of the matrix. K labels the row of the particular matrix. L labels the L non-zero element. And then we just put the value of this L non-zero element of the kth row of the Jth matrix in the 4th register. Okay, so that's just a standard thing. Okay, so there is something good about this algorithm. First, it has an unconditional quadratic speedup in terms of either n or m, not both at the same time, that we don't know, right? Because I showed you this classical lower bound of n plus m. And it's not so far away from optimal in the quantum case, right? With everything else constant, we need at least times square root of n plus square root of m. So that's there is some room for improvement, but not so much. There's some also really bad parts. The dependence on the other parameters, they are terrible at the moment. Okay, so they are like the product of small r with big R to the power of 32 and error 1 over r to the power of 18. So not very practical. So, but hopefully we have time to fix this until we have a quantum computer. So, but yeah. So I think that I think that just improving our analysis should be able to improve this a lot. But also, if we really want to get this to some very small values, we might have to use some new ideas. So that's a good open problem. And a bad thing is also that it's close to optimal, right? So in general, we won't have super polynomial speedups here. Okay, so the best thing we can expect in general, in the worst case, are polynomial speedups of the form that we have here. Okay, that's one result. Just a special case. We are going to get to that more later. If the SDP has the property that all the coefficients are bigger than 1, the BJ coefficients, then this dependence on the size of the dual solution drops out, so we don't have it anymore. Okay, so that's just one observation. All right, so now a second result. So suppose we cannot have larger speedups in general, but can we have some, in some instances? So when can we have larger speedups? And we have a result on that. So we also have a quantum algorithm for solving SDPs, and it runs in time T Gibbs. We get to that. This is the crucial number. Then square root m in terms of the number of constraints, we don't improve it so much. But now there is only polylogarithmic dependence on n, and that's the important thing. So what is this T Gibbs? This roughly is just the time we need on a quantum computer to prepare some family of quantum states, which we call Gibbs states, and they are of this form. They are just exponential of linear combination of the input matrices of the problem, right? So A, I, and C, they are the input matrices of the problem. These new I coefficients, they are just some real numbers that we have to vary over them. If we can prepare this kind of Gibbs states efficiently for any choice of new I's coefficients which are not so big, they are like smaller than other log n poly 1 over delta, then then that's the leading order of the performance of the algorithm. So what this means is that we can just now use quantum Gibbs sampling. For example, we could use quantum metropolis as a heuristic here, right? So usually it's very hard to analyze how quickly a system thermalizes. We're interested in understanding how, we can think of this linear combination of the input matrices as a quantum Hamiltonian, and we understand how quickly we can prepare the Gibbs states. That's a hard problem, but maybe if we have a quantum computer, we can just try and see if we have a good job. And if we're lucky and the thermalization is quick, what I mean quick is just like polynomial in the number of qubits here, which is now polylog in n, because n is the dimension of the matrix, then we can have larger speedups. And I think that's nice, because this gives an application of quantum Gibbs sampling outside just simulating thermal properties of physical systems. So we know classical Gibbs sampling is a very useful algorithmic tool. This gives, I guess, one example in the quantum case as well. All right, so now we have an instance where we can have these larger speedups, where we can prove we have these larger speedups. But I think it's a bit contrived, but I think it's still interesting. Let me tell you how it is. And it's when we have these matrices as like quantum data. So the result is that we also have a quantum algorithm for SDPs that runs in times square root of m, but now polylog n and the other parameters. And we have a new parameter, which is the rank of the matrices. If the matrix, if the data is given in quantum form. So what is that? We assume there is an oracle that given I outputs not an entry of I anymore, but outputs the eigenvalues of AI, and output also the eigenvectors as quantum states. Just prepare these quantum states. And we assume rank is just the maximum rank of all the matrices. So this works well when the matrices are low rank, such that we can just write down all the eigenstates as quantum states and all the eigenvalues. Okay, and the idea is very simple. I won't get to that, but it's just because of these two assumptions, low rank and quantum data, you can show that on a quantum computer we can just easily prepare the Gibbs states that we need. We can just do the Gibbs sampling efficiently. And that's how it works. So in times poly, log n, and rank of the matrices. Of course, the limitation is not clear how relevant this is, and also it's not clear how we should compare this with classical methods, right? But I think it shows that we might have bigger speedups some cases. So now what I want to do is to give you an idea of how to get this algorithm. And I want to start with a special case of SDP, which is well understood already, and probably many of you know how to do it, which is to compute the maximum eigenvalue of a matrix, of a sparse matrix. So computing the maximum eigenvalue of a sparse matrix C is a semi-definite program. It's just this one, extremely simple, right? We just maximize trace X such that the trace of X equals 1 is a density matrix, right? So, and X is bigger or equal to 0. So this gives the maximum eigenvalue. This is a well-studied problem, right? So, okay, many times we study the minimum eigenvalue is the same. We just do for minus C. And one way to do that, right, the heuristic way, of course that's a hard problem in general, right? It's like QMA hard, but we can still try to do it sometimes. And one interesting way of doing that is using quantum annealing, and we just cool down the Hamiltonian, right? We just cool down minus C, try to do the ground states. And it's easy calculation. If you can prepare the Gibbs states, e to the beta C, for some inverse temperature of order log n over delta, then we can compute the maximum eigenvalue to error delta. Okay, so if we can cool down to sufficiently low temperatures, we can solve this problem. Of course, not always we can. But now let me just tell you how these square roots are appearing in the complexity. In the worst case, they already appear here, and this was analyzed, I think, first by Poulan and Vossian, and there are many other papers since, giving different alternatives or just improving parameters. So the result is that you can actually prepare these Gibbs states for S sparse C in time roughly, this O tilde means that there is some hidden poly log factors, but in times roughly sparsity times square root n on a quantum computer. So naively you could do that in times S times n, right? But a quantum computer have this square root speed up. And the idea is pretty standard. Actually, you just use phase estimation and amplitude amplification. So let psi I be the eigenstates of C and I the eigenvalues. Then what you could do, you prepare the maximum entangled state. You can write the maximum entangled state in any base you want. You write in the eigenstate basis. So it's this sum over I, psi I, psi I. I'm not putting normalizations here. Then you do phase estimation, and you just learn, you just write down the value of the energy associated to the eigenstates. Then you just do the operation with, like, you have an extra ancilla. If the ancilla is 0, you just put this Boltzmann weight in front. If it's 1, you put the other thing to be a normalized state. And what you can show is that if you just post-select on the ancilla qubit being 0, you get a purification of the Gibbs state, which is what you want. But of course, the probability is small. The probability, if you do the math, will just be of order 1 over n. It can be bigger sometimes, but the worst case will be of order 1 over n. Now what you can do is just use amplitude amplification to boost to getting the purification with a very good probability. But you need a number of interactions, which is like roughly square root 1 over probability, so it's square root n. So that's the idea. And to get this worst case performance, basically what we like to do is something very similar to that, but for general SDPs, right? And then what is not clear is how we can solve general SDPs basically just by preparing quantum Gibbs states, and this is what I want to explain you how to do. And luckily this, this was done for us in parts classically. There is an algorithm by Arora-Kale, which is, if you read it, is really there is like some quantum Gibbs states there, and therefore that was our motivation for looking at it. So the quantum algorithm is based on a classical algorithm for SDPs due to Arora-Kale from 2007. It's based on these multiplicative weight methods. I want to review their methods, but just for now, we're going to assume that BI's are all bigger than 1. And the general case, there is a reduction, which just reduces any case to this case, but there is like this extra blow-up complexity of order poly R, but we are not going to consider that. And because we have this R parameter, we can, without laws of generality, just assume that the first matrix is identity, and the B1 associated to it is just R, right? This just gives the constraint that trace X is smaller than R, which by definition is true, by the definition of R. All right, so let me tell you the algorithm. But in the algorithm, there is a subroutine, an auxiliary algorithm, which is called the Oracle. And this is a very simple linear programming with just 2 constraints. Let me tell you what it is. This is just an oracle of a density matrix rho, just searches for a vector y, which satisfies 2 constraints. One y should belong to a set, the alpha, which is the set of all vectors for which all elements are bigger than 0, and the inner product of by is smaller than alpha, where alpha is a parameter that I'm going to show you how to choose later. And there is another constraint, which if you notice is just the positive semi-definite constraint of the dual problem is sum over j, aj, yj minus c is bigger or equal to 0. Here we're just taking the trace of that with rho. This should be bigger than 0. So it's kind of, we are relaxing the PSD constraints that we have on the dual program just to some linear constraint now. Okay, so we have, it's an LP with 3 constraints actually, right? Right, so let's think about how to solve this oracle later, but what is the algorithm? So there, you start from some density matrix, which is the maximally mixed one, rho 1. Then we have some error parameter, epsilon, which depends on the accuracy delta, and this R parameter. And we iterate t times, and t is roughly R squared ln n over delta square. And what is this iteration? Well, first you just run oracle on the matrix rho t, and you get this vector yt. Then you construct some matrix which depends on y, t, and on the input matrices, mt. Then you compute the Gibbs state of this matrix, which is rho t plus 1, right? That's just the Gibbs state associated to this, well, to the sum of the previous Hamiltonians. And you iterate that, like logarithm many times. And in the end, you output some y, which is the average of the yt, plus some correction just to make things work. And this will be a good solution. So what they show is that this y bar, the inner product is close to the is always, this should be 1 plus delta times alpha. So alpha, imagine just a guess for the optimal solution, and we just vary alpha by binary search to get the optimal solution. And this shows, again, there's a type, it should be like bigger than 1 plus delta, everything times alpha. Okay, so you're close to, you can certify that you're smaller than alpha up to some small error. How much time do I have, Aaron?
7 minutes.
Okay, so maybe let me, I don't know how much we get to the quantum algorithm, but we have to do the classical before. So why this works? So first, it's easy to see why this y bar has a small objective value, right? So by definition, all elements are bigger than 0, so that's good. The inner product is also smaller than alpha. So if you just do the map of the inner product of y bar with b, you have this small correction which gives delta times alpha, and then all the other terms here, all the yt times b, by definition they are smaller than alpha, so you get the objective value is not too big. That's good. But what we really care about, well, the harder thing is whether the positive semi-definite constraint is satisfied. So we must check that y bar is feasible. And for the oracle, we know that the expectation value of this matrix, sum over j, y, jt, aj minus c, on rho t is bigger than 0. But what we need is that this matrix is positive semi-definite. So we want to boost from being, for the trace on some matrix being bigger than 0 to the trace on all matrix being bigger than 0. And this is what this matrix multiplicative weight method does for us. There are many instances of it. We are interested in a matrix version of it here. So we are given, what it says, we're given n by n matrices, m of t, and some error. And then you can bound, so here we just take the average of the expectation value of rho t with mt. And it is always smaller than some small term, 1 plus epsilon, times the minimum eigenvalue of the average of the matrices, up to some additive correction, which when t is bigger goes to 0. So this says that if you want to certify that the sum of the matrix, or the average of the matrices is positive semi-definite, you can do that just by computing the expectation value on this matrix rho t, right? And what is rho t is just the Gibbs states of the sum of the matrices. So this is exactly what we need. There is an interpretation in terms of a two-player zero-sum game that I won't get into that. But you see the flavor, right? Why this works. From the oracle, we know that this expectation value on rho t is bigger than 0. But because of this MMW method, this implies that actually the whole matrix is positive semi-definite, which is what we want. Okay, so I'm running out of time. Let me just roughly sketch what we change in this Arora-Kale algorithm to get the quantum version. So we make it quantum as follows. So first we implement oracle where we have to implement this oracle. Okay, we do it by Gibbs sampling as well. So we show that we can also map this linear program to a Gibbs sampling problem. And then we do that to produce this vector YT. And we apply amplitude amplification to solve this in time, roughly the main complexity of the algorithm. And I show you why this is the complexity at this step. There is also another step. These MT, they are not really, they are some of sparse matrices, but there are many of them. So the overall wouldn't be that sparse. And of course, to implement Gibbs sampling efficiently, we need a sparse matrix. So we just sparsify it. We just do some random sampling. And we get some some bar empty matrix, which is associated to the original empty matrix just by, instead of having a YT vector here, we just sample from a distribution given by the normalized YT. And then we can show they are still closed, the matrices, so that's fine. And we do Gibbs sampling again for the row T. We prepare this as a quantum states, but now for the sparsified version. And this has time. This is S squared times square root of n. So why we get this complexity, let me just explain a little bit more. So what we can show, and I won't be able to tell you, but that there is always a feasible YT. This follows from James' principle of max entropy, basically, of the form some normalization n times the probability distribution QT, which is of the Gibbs form. And we know what is the Gibbs, what is the Hamiltonian of the Gibbs states. It's just two coefficients, lambda and mu, that we have to vary over. They are real coefficients that we don't know what they are. We just brute force search them. But times the constraints of the LP, right? One constraint is the trace AI rho T, and another constraint is the BIs, right? So we can just, what we have to do is prepare Gibbs states of this form. But okay, so we can do Gibbs sampling and amplitude amplification here. That's fine. But to do that, we need the oracle to the entries of H, right? And if you see the entries of H, they depend on a quantum state rho T that we also have to prepare. So here what we have to do to simulate the oracle to the entries of H, we have to prepare the states rho T and measure them with the observables AI, depending on the entry that we want to estimate. So what is the time for that? Well, to prepare each rho T, right? This is just like normal Gibbs sampling. This takes times roughly S squared square root of n. But to sample QT, to sample QT doing amplitude amplification and Gibbs sampling, this requires roughly square root m oracle calls to the oracle for H. So each call to the oracle of H takes times roughly S square root of n, so we get a total complexity. So that's very roughly how it appears. I have to, maybe I will not tell you about that. Let me just do the conclusion of the open problem. So I show you that quantum computers provide speedups for SDPs, but there are many things that has to be improved. Okay, thank you. So one, right, we can improve the parameters like this small, big R, small r, and delta. They're really bad performance at the moment, right? I think there is a lot of room for improvement, but it would be interesting to see what the limits are. Also, can we find the optimal algorithm in terms of n, m, and s? It's kind of close, right, the lower and upper bound, but there are gaps, so it would be nice to close these gaps. Second, can we find some relevant settings where there are super polynomial speedups? That will be very interesting. Maybe we might have to wait until we have a quantum computer, but maybe not. Maybe we can understand this better. Also, a very interesting feature of the algorithm is that we only use a quantum computer to prepare Gibbs states. Okay, so and then we can think, and Gibbs state and the temperature is not so small. It's like is small, but it's not like zero temperature. So maybe there is some inherent robustness to error of the algorithm that we could explore. And I don't know. That's an interesting question. And related to that, if we can improve the parameters, and if there is a robustness to error, right, because the quantum computer is only used for Gibbs sampling, is there potentially a nice application for a small size quantum computer? Could we actually run this if we have some small size quantum computer with no error correction? That's also a question that I would like to explore more. So that's it. Thank you.
So we have plenty of time for questions. Wow. Yeah, Murphy? Actually.
Is there a simple reason you choose the specification of M, of the matrix, to be log of order log M? And if you change the scaling, will it affect your scaling of big R?
Can you repeat the question, please? This log M, what do you mean, like?
There's, because in second step.
Was it this? Like a log or
right,
some? Yeah.
The specification Is there a simple reason you choose to sparsify it to log n m?
I mean, log m is what we have to specify for the two matrices to be close to each other. And it's also good for us because this log m factor is, we don't care about it because it's much smaller than than the square root m factor that we have anyway. So that's why I was happy with it. But actually, you need at least this log m. If you not do this log m, then it's specified too much and they are not close anymore. But this log m is also good enough for us, right? Because it's very small.
Well, my question is about your last comment in your conclusion. So can you think of like application of SDP where it's obvious that the way the output is given by just sampling, where it can be useful?
Or just
like some classical problem where that would be enough?
Yeah. I'm not sure, but I mean, you learn. I mean, because you always learn the optimal value at least, right? So you, but I don't know.
Actually, I have a question which may be an answer to that.
Yeah.
So I was thinking about cases when you want to have a high dimensional SDP where the entries are succinctly described. Mm-hmm. So one example of this is the DPS hierarchy for searching for over separable states. Have you thought about how that fits into these parameters?
Yeah, right. So the problem is, I should have mentioned that, but because the very bad depends on the small r and big R, usually for applications we are not getting speedups. Mm-hmm. So that's a drawback. So we have to improve on that before we can start applying to so like specific SDPs and getting improvements.
I also have a related question. So how precise do we have to specify all these entries, and how hard is this to actually, will this affect the running time?
You mean if you have an error in the entries of the input matrices, how it affects?
Yes.
Yeah. So that's why I think you relate to this robustness to error. So you care about Gibbs states at So suppose let's just normalize like in the physics way, right? Suppose the Hamiltonian scales of the number of particles. That's normalization. Then the temperature would just be something a constant proportional to the 1/error that you want. So very small but constant temperature. Now imagine that you just have some perturbation in the Hamiltonian. Then the question is how much it affects the expectation value of the Gibbs states on some on some matrices, and sometimes it can be bad, but I think many times it will be okay, right? So I feel there is reason to be hopeful, I think, but it remains to be seen.
Can you
Do you think the dependence on the sparsity should be polynomial, or do you think you can get some speed up for dense matrices?
So it should be polynomial, and there is also by like Ron DeWolf and his collaborators, they also have this. There's a simple and nice argument that this S square is necessary. So.
Any other questions?
Hi. So you're using this amplitude amplification to quadratically speed up some of the algorithms that you're using here, right?
Yes.
So in some other scenario, let's say, for example, measure and replace, where you want to prepare ground state of some two projectors. Could you also use amplitude amplification to get quadratic speedups there?
To prepare ground states?
Like, for example, in measure and replace algorithm, let's say.
I don't know what the measure and replace is, but yeah, there is also similar results to prepare the ground state of a many-body Hamiltonian, and you can do also in square root n time.
I see. Okay,
yes.
Cool. All right.
It's by, I think, Davi as well, right?
Okay, if there are no more questions, let's thank Fernando again for a nice talk.
Thank you.